What if the universe could forget, not in the way you or I misplace a memory, but a true and total erasure, a permanent deletion from the cosmic record? Imagine a story, your story, every intricate detail of your existence, from the atoms that formed you to the thoughts that defined you, being meticulously written into the grand book of reality. Now imagine a place capable of taking that book, that singular, irreplaceable narrative, and burning it so completely that not even the ash of its meaning remains. A place that doesn't just end the story, but ensures it can never ever be retold, not even by the laws of physics themselves. This is not a philosophical fancy. It is the single most terrifying and profound question in all of modern science, a question posed by the most extreme objects we have ever conceived. It is a paradox born in the heart of a gravitational monster, a place where our understanding of everything we thought we knew about the universe comes to a violent and spectacular halt. Out here in the silent, unforgiving emptiness between the stars lurks a perfect darkness, an absolute black. It is a rupture in the fabric of space-time, a gravitational cataract blinding a patch of the heavens. We call it a black hole, but that name, simple and direct, belies the sheer existential horror of its nature. For decades, we saw them as cosmic vacuum cleaners, monstrously simple objects defined only by their mass, their spin, and their charge. They were the final silent punctuation mark at the end of a massive star's life. But this simplicity was a mask, a placid surface, hiding a raging theoretical storm beneath. The conflict it represents is a war for the very soul of physics, a battle royale between the two towering achievements of the human mind. On one side stands Albert Einstein's masterpiece, the general theory of relativity. It is a vision of the universe as a grand, sweeping tapestry of space-time, a four-dimensional cosmic ocean. In this ocean, planets and stars are not pulled by a mysterious force, but follow the curves and dips created by the weight of other objects like marbles rolling in a warped sheet of rubber. Relativity is elegant, deterministic, and profoundly beautiful. It paints a picture of a reliable clockwork cosmos where cause and effect are bound by immutable law. And it is this very theory that predicts with chilling certainty the existence of black holes. It tells us that if you concentrate enough matter into a small enough space, the curvature of space-time becomes infinite. It punches a hole through the fabric of reality itself, creating a one-way door in the universe. Crossing its threshold, the event horizon is not a journey you can resist. Space-time itself flows inward faster than the speed of light, carrying you inevitably toward a central point of infinite density, the singularity. According to Einstein's equations, anything that falls in a star, a planet, an astronaut's lost photograph, has its physical form crushed into this infinitesimal point, its identity lost forever to the outside universe. All of the intricate, unique complexity that made it what it was is seemingly homogenized, blended into the featureless mass of the black hole. Relativity offers no escape and, most critically, no record of what was lost. The black hole in Einstein's world is the ultimate dead end, a place where the universe's past is brutally and efficiently severed from its future. It is a perfect information incinerator. And on the other side of this intellectual battlefield stands the strangest, most successful, and most counterintuitive theory ever devised: quantum mechanics. This is not the majestic, sweeping cosmos of Einstein. This is the universe at its most fundamental granular level, a bizarre and chaotic world of particles that pop in and out of existence, that can be in multiple places at once, that are governed not by certainty, but by shimmering clouds of probability. Where relativity is a symphony, quantum mechanics is a frenetic, unpredictable jazz solo. Yet for all its weirdness, it is the bedrock of our modern world, the theory that gives us computers, lasers, and nuclear energy. And at the very heart of this chaotic quantum world lies a single, non-negotiable, absolutely sacred law: the conservation of information. This principle states that information in its purest physical sense can never ever be destroyed. It is one of the deepest tenets of reality. It doesn't refer to the words on a page, but to the unique quantum state of every single particle that makes up that page. The spin, the position, the momentum of every atom. This quantum information is the universe's ultimate fingerprint, the unique signature of an object that distinguishes it from everything else. You can burn the page, but the quantum rules insist that if you could meticulously collect every wisp of smoke, every photon of light, every vibrating atom of heat, you could in principle perfectly reconstruct the original page. The information isn't gone. It has merely been scrambled, transformed into a different, more chaotic form. It is the universe's promise that nothing is ever truly lost. For most of the 20th century, these two great theories lived in a state of uneasy truce. Relativity governed the very large, the graceful waltz of galaxies, the bending of starlight, the expansion of the cosmos. Quantum mechanics ruled the very small, the frantic dance of electrons, the structure of atoms, the fundamental forces of nature. They were like two separate legal systems for two different countries. But the black hole is where their jurisdictions violently overlap. It is both fantastically massive, the domain of relativity, and at its core it contains a singularity, a point of infinite density where quantum effects must surely reign supreme. The black hole is the arena where these two titans of physics are forced to confront one another, and their encounter is not a peaceful one. The confrontation gives rise to a paradox so profound it threatens to shatter our most basic understanding of reality. Relativity insists that the black hole is a perfect vault, an information tomb from which nothing can ever escape or be recovered. The unique, intricate story of whatever falls in is wiped from the cosmic slate. Quantum mechanics, with equal and opposite convictions, screams that this is impossible. It declares that the universe is forbidden from keeping such secrets. The story must be preserved somewhere, somehow. One of them has to be wrong. One of these pillars of modern science, which have been tested and verified to astonishing degrees of accuracy in their own domains, must break when faced with the abyss. This isn't merely an abstract philosophical debate for scientists in ivory towers. The outcome of this clash has profound implications for the nature of our reality. It asks, is the universe a fundamentally logical place? Does the past uniquely determine the future? Or can the universe simply and arbitrarily forget its own history? For a long time, the paradox was a curiosity, a theoretical puzzle simmering on the back burner of physics. Many believed the information wasn't truly lost, but was simply locked away inside the black hole's event horizon, hidden from our view but still existing within the universe. If you can't get the information out but it still technically exists inside, perhaps the quantum laws are bent but not broken. This was a fragile piece, a way to let both theories save face. But then in 1974, a young Stephen Hawking, aiming to unite the two theories, made a startling discovery that blew this fragile piece to pieces and elevated the information paradox from a mere puzzle to an existential crisis for physics. He proved that black holes are not in fact completely black. He showed that due to the strange rules of quantum mechanics playing out at the edge of the event horizon, black holes must leak, they must radiate. Very, very slowly, over unimaginable timescales, they glow with a faint ethereal energy. This phenomenon, now known as Hawking radiation, meant that black holes were not eternal prisons. They were mortal. They evaporate. Hawking's discovery was a thunderclap. It transformed the very nature of the problem. A black hole that exists forever could, in theory, hold on to its information forever, keeping the quantum accountants happy. But a black hole that evaporates presents an apocalyptic scenario. Imagine a library of cosmic knowledge containing the story of 1 trillion suns being swallowed by a black hole. For eons it sits there, leaking away its mass photon by photon into the void. Over timescales that dwarf the current age of the universe, it shrinks. The gravitational grip weakens. Finally, in a final quiet puff of radiation, the black hole disappears completely. It is gone. And if the information about that library was trapped inside it, then the information is gone too. Not just hidden, not just scrambled, but utterly, completely and irrevocably annihilated from reality. The universe would have performed the one act that quantum mechanics says is forbidden. It would have forgotten. Hawking's initial calculations were devastating. They showed that the radiation escaping the black hole was thermal. It was a random, featureless hiss of energy, like the static between radio stations. It contained no trace, no echo, no ghost of the unique and complex things that had fallen in. A black hole that swallowed a star would produce the exact same kind of radiation as one that swallowed an encyclopedia or a spaceship or a planet teeming with life. The outgoing radiation was gibberish. It told you nothing. The story was gone. This conclusion was so shocking, so contrary to the core principles of physics, that it triggered a 40-year war of ideas that is still raging today. It was a declaration that one of our most trusted maps of the universe leads directly off a cliff. The implications were staggering. If information can be destroyed, then causality itself is in jeopardy. If the past can be erased, then the future becomes fundamentally unpredictable, not just in practice but in principle. The deterministic clockwork universe of Einstein would be a mirage, and at a fundamental level, reality would be governed by a terrifying lawlessness. The very idea that we can understand the universe through logical rules would be thrown into question. Physicists were faced with a choice between three impossibilities. Either Einstein's theory of gravity and space-time is wrong at the event horizon, or the sacred tenets of quantum mechanics are not so sacred after all, or there is a third, even stranger possibility that we have yet to uncover. Stephen Hawking, a man whose intuition was forged in the crucible of Einstein's relativity, was initially adamant. He placed a public bet with fellow physicists, wagering that information was well and truly lost. He was, for a time, a champion of chaos, arguing that the universe had a fundamental leakiness, a built-in forgetfulness. But physics is not a discipline that accepts paradoxes lightly. A paradox is not a feature of the universe. It is a signpost pointing to a profound gap in our knowledge. It is a siren call from the cosmos, telling us that our theories are incomplete, that there is a deeper, more elegant truth waiting to be discovered. To solve this enigma, we have been forced to tear down our most cherished notions of reality. We've had to question the very nature of space and time. We've been forced to entertain ideas that sound like pure science fiction, that our three-dimensional universe might be a hologram projected from a distant two-dimensional surface, that the inside of a black hole might be connected to other universes through wormholes, or that the event horizon is not an empty gateway, but a raging wall of fire that incinerates anything on contact. Each proposed solution is more bizarre than the last, and each one attempts to find a way to encode the story of what falls in onto the faint whisper-thin radiation that leaks back out. The quest to resolve the black hole information paradox is nothing less than the search for a new theory of everything, a quantum theory of gravity that can finally unite the two warring factions of physics into a single coherent description of reality. It is a search that takes us to the absolute limits of what is knowable, to the very edge of space and time. Before we can even begin to explore these radical, mind-bending solutions, we must first understand the battlefield more intimately. We must journey back to that precipice, that shore of a one-way river flowing out of our universe, the event horizon. For it is there, at the boundary between the known and the unknowable, that the universe's greatest secret is hiding. The war for the soul of physics has begun, and the prize is the answer to that one terrifying question. Does the universe have a memory, or is it doomed to an ultimate cosmic amnesia? The clues, it turns out, may not lie in the darkness, but in the faint glow that surrounds it. What happens when a law of nature turns on its creator? In 1915, Albert Einstein unveiled a masterpiece, a new vision of the cosmos, not as a static stage, but as a dynamic, flowing fabric of space-time. His equations of general relativity were elegant, powerful, and described a universe where gravity was no longer a mysterious force, but the simple consequence of matter bending the reality around it. Planets were not pulled by the sun. They were following the straightest possible path through a valley in space-time carved by the sun's immense mass. It was a revolution in thought, a theory so beautiful it felt like uncovering the universe's own poetry. But hidden deep within the exquisite mathematics, tucked away in its most extreme solutions, was a monster. A prediction so bizarre, so utterly violent and absolute, that Einstein himself would spend the rest of his life refusing to believe it could be real. His theory, the work of his genius, had inadvertently written a prophecy of hell. It predicted a place where all laws would be crushed into nothing. The first man to truly stare into this mathematical abyss was not working in a pristine university office, but in the freezing mud of the Russian front during the First World War. Karl Schwarzschild, an astronomer and physicist serving in the German army, somehow found the clarity amidst the cacophony of artillery to solve Einstein's complex field equations for a single non-rotating spherical mass. His solution, sent to Einstein from the midst of chaos, was the first exact answer the new theory had ever produced. And it was terrifying. Schwarzschild's math showed that if you could squeeze enough matter into a small enough space, the curvature of space-time would become infinite. It would in effect tear a hole in itself. He calculated a specific boundary for any given mass, a critical circumference from which there could be no escape. This boundary, which we now call the Schwarzschild radius, was more than a mathematical curiosity. It was the blueprint for a prison unlike any other. A prison where the walls are not made of stone or steel but of warped geometry, and the jailer is gravity itself magnified to an impossible, inescapable strength. For a star like our Sun, this point of no return would be just under 6 kilometers across. For the Earth, it would be the size of a marble. For decades, the scientific community treated this idea as a grotesque fiction, a mathematical ghost. The prevailing wisdom was that nature would surely intervene. Some unknown pressure, some new force would always halt the collapse, preventing the formation of such a pathological object. The universe, they argued, could not be so perverse as to allow such a thing to exist. Even Einstein, the progenitor of the idea, found it abhorrent. He believed it was a flaw in the theory, a sign that it broke down under extreme conditions, not a prediction of a new and terrible kind of celestial body. The notion of a star collapsing forever, shrinking to an infinitely dense point, seemed like a failure of physics, not a feature of the cosmos. Yet the universe is under no obligation to conform to our sense of comfort or reason. The evidence that it was in fact this perverse began to mount not from astronomers peering through telescopes, but from theorists scribbling on chalkboards following the cold hard logic of numbers to their ineluctable conclusion. The first crack in this wall of disbelief came from a young Indian physicist on a steamship bound for England. In 1930, Subramanian Chandrasekhar calculated the fate of dying stars of a certain mass known as white dwarfs. He discovered a fundamental limit, an absolute tipping point. He proved with stark mathematical certainty that any white dwarf more than about 1.4 times the mass of our Sun would be unable to support itself against its own gravitational pull. It had no choice. It had times to collapse further. Nature, it turned out, did not have a safety valve. This was a profound and disturbing revelation. The universe wasn't just capable of creating these gravitational prisons. For the most massive stars, it was mandatory. Then, in 1939, on the very eve of a new world war, two physicists at Berkeley took the next logical step. Robert Oppenheimer and his student Hartland Snyder considered what would happen to a star far more massive than Chandrasekhar's limit, a star with no force left to fight its own demise. Their paper, titled On Continued Gravitational Contraction, was one of the most chilling documents in the history of science. It described in the dispassionate language of physics the birth of the monster. They calculated that as the star collapses, the gravity on its surface becomes so intense that it begins to radically warp time itself. For an observer watching from a safe distance, the star's light would become redder and dimmer, its final moments stretched out, slowing down as it approached that critical Schwarzschild radius. The dying star would appear to freeze at this boundary, its image painted on the edge of the abyss for eternity, fading slowly into blackness. But for the star itself, for any matter falling with it, there is no slowing down. There is no pause. The crossing of this threshold is an event in space-time as real and as final as any other. This boundary, this one-way membrane separating our universe from a place of utter oblivion, is the event horizon. It is the defining feature of a black hole. It is not a physical surface you could touch. It is a point of pure geometry, a location in space. It is the precise place where the gravitational pull becomes so overwhelming that the escape velocity, the speed you need to break free, surpasses the speed of light. And since nothing in the universe can travel faster than light, the event horizon marks the point of no return. Once you cross it, all paths, all possible futures lead in only one direction, inward. Imagine you are in a spacecraft approaching this silent, invisible precipice. Outside, the universe of stars you knew is being distorted, light bending around the immense gravitational well ahead. You see multiple images of the same galaxies, their light taking different paths to reach you. You decide to turn back. You are still outside the event horizon, so you fire your engines. With enough power, you can still escape. Your journey away is a struggle against a colossal cosmic tide, but escape is possible. Now imagine you miscalculated. You drift just 1 meter too far. You have crossed the line. You are inside. Nothing has changed in your immediate vicinity. There was no sound, no flash of light, no wall to break through. Your ship's instruments read normal. But when you fire your engines now, something is profoundly wrong. Even at full thrust, even if you had an engine capable of infinite power, you do not move away. You cannot even hold your position. You are still falling. Because here inside the event horizon, space itself is falling. The very fabric of reality is flowing inward toward the center faster than the speed of light. To try and fly out would be like trying to run up a waterfall that is flowing faster than you can possibly run. It is a physical, geometric, and absolute impossibility. You are no longer a traveler in the cosmos. You have become cargo on a one-way trip to annihilation. The journey from the event horizon to the center is not a gentle one. The same force that holds planets in orbit and keeps your feet on the ground, gravity becomes a weapon of unimaginable violence. Because you are a three-dimensional object, the black hole's gravity does not pull on you uniformly. It pulls more intensely on the parts of you that are closer to the center. If you are falling feet first, the gravitational force on your toes is exponentially stronger than the force on your head. This difference, this tidal force, begins to stretch you. At first it might feel like a gentle tug, but the feeling would escalate with terrifying speed. Your body, your ship, anything with physical extension would be pulled apart, elongated into a thin stream of atoms like toothpaste being squeezed from a tube. This brutal final act of disintegration is what scientists with a touch of grim poetry call spaghettification. You would be rendered into a filament of your former self, a stream of fundamental particles all flowing along the current of collapsing space-time toward the final destination. And it is there, at the very heart of the black hole, that we confront the true limit of our understanding, a concept that defies language itself, the singularity. According to Einstein's classical theory, all the matter that has ever fallen into the black hole, entire stars, planets, asteroids, and your own spaghettified remains, is crushed into a region of zero volume and infinite density. Think about that. Not just small, not just dense, but a point with literally no size that contains a mass potentially greater than millions of suns. At the singularity, the elegant equations of general relativity, the very source code of our universe, break down completely. They produce answers of infinity, which is the polite way mathematics has of screaming that it no longer makes sense. Here, space and time as we know them do not simply warp. They cease to exist. There is no before or after at a singularity. There is no here or there. All the known laws of physics, causality, thermodynamics, the conservation of energy, are ground into dust. It is the universe's ultimate dead end, a place where reality comes to a full and violent stop. It is a cosmic tomb in the truest sense of the word. But the horror of the classical black hole is not merely physical destruction. It is something far more profound, something that strikes at the very soul of existence. Physics is built upon one sacred, unbreakable principle, that information can never be truly destroyed. You can burn a book, but in theory, if you could track every particle of smoke, every joule of heat, every photon of light emitted by the fire, you could piece the information in that book back together. The story is not gone. It is merely rearranged into a more chaotic state. You can shatter a vase, but the information about its original shape, its color, its material, is still encoded in the arrangement and energy of the resulting shards. The universe, we have always believed, keeps meticulous records. It never forgets. But the classical black hole violates this fundamental law. When matter crosses the event horizon and is crushed at the singularity, the information it contained is believed to be erased from the universe forever. The unique quantum arrangement of the atoms that made up a star, the specific history of a planet, the complex web of electrical impulses that constituted your thoughts and memories, all of it is gone, not just rearranged, but deleted from the cosmic hard drive. The story of you written in the language of atoms is not just over, it is as if it were never written at all. This is the ultimate violation. The black hole does not just kill you, it unmakes you. It devours your very existence, leaving not even a ghost of data behind. This is the classical view, the monster born from Einstein's beautiful equations. A perfect prison from which nothing, not even light, can escape. A perfect executioner that doesn't just destroy matter, but annihilates the very information that defines it. For much of the 20th century, this was the accepted truth. These objects were the universe's silent, gluttonous, final resting places, cosmic sinkholes that patiently wait to consume and erase anything that strays too close. They were aberrations perhaps, but they were a manageable, predictable kind of monster, confined by the clear, sharp lines of their event horizons. But this chillingly simple picture of a perfect information-destroying void would not prove to be the final word. The universe, it turns out, is infinitely more clever and far more strange than even this nightmare scenario would suggest. And as we began to probe the true nature of these gravitational ghosts, we found that the neat boundary of the event horizon might not be the simple end of the story we once thought. It might instead be the beginning of an entirely new and far more unpredictable set of rules. Rules that are being put to the ultimate test right now by a lonely wanderer from interstellar space, a comet named 3I, Atlas, as it charts its own fateful course toward the most dangerous frontier in the known universe. To truly comprehend the abyss that awaits 3I, Atlas, to understand what happens when cosmic architecture is brought to its knees, we must pivot from the immediate terrifying spectacle of a world being shredded. The drama unfolding in our solar system is but a symptom, a visible tremor from a much deeper, more fundamental fault line running through the heart of reality itself. The finality we fear, the spectre of annihilation, forces us to confront not just the death of a celestial body, but the very rules that govern existence and destruction. We must journey from the macro to the micro, from the crush of gravity to the whisper of quantum mechanics. And that journey begins with a mind that dared to voyage, where light itself could not the mind of Stephen Hawking. His name is now etched into the pantheon of science, his synthesized voice a symbol of intellect transcending physical limits. But in the early 1972, he was a young, brilliant physicist embarking on a quest that many considered a fool's errand. He sought to reconcile the two great pillars of modern physics, the warring titans that described our universe. On one side stood Einstein's general theory of relativity, the majestic sweeping law of the large. It governs the ballet of planets, the curvature of space-time, the inexorable pull of a black hole. On the other stood quantum mechanics, the strange, probabilistic and wildly successful theory of the small, describing the chaotic dance of particles that form the bedrock of everything we see. These two theories worked perfectly in their own domains, but at the boundary where they met inside the singularity of a black hole, or at the moment of the Big Bang, they broke down, spewing mathematical nonsense. They refused to speak the same language. Before Hawking, the black hole was a simple, brutal object defined by relativity alone. It was the ultimate prison, a one-way door in the universe. Anything that crossed its boundary, the event horizon, was lost forever, its story erased. The physicist John Wheeler had famously declared that a black hole has no hair, a beautifully concise idea, meaning that no matter how complex an object you throw in a star, a spaceship, a library of every book ever written, the black hole only remembers three things: its mass, its spin, and its charge. All the intricate details, all the rich complexity, all the times information, times that made up the object was seemingly wiped from the cosmic ledger. The event horizon was seen as an absolute barrier, a perfect causal shield. The black hole was a silent, eternal, and unchanging gravitational tomb. It was a place where physics went to die. But Stephen Hawking was not satisfied with this cosmic eulogy. He suspected that this ironclad separation between the gravitational world of Einstein and the quantum world of particles was not the full story. He began to wonder what would happen if you considered the bizarre rules of quantum mechanics not inside the black hole, but right at its very edge, in the seemingly empty space surrounding the event horizon. This was a heretical thought. It was like asking what happens when an irresistible force meets an immovable object. The vacuum of space, according to quantum field theory, is not empty at all. It is a turbulent, roiling sea of potential, a cauldron of fleeting existence that physicists call the quantum foam. Imagine it. Everywhere, at every moment, for infinitesimally small fractions of a second, the universe is borrowing energy from itself. This energy debt allows for the spontaneous creation of a particle and its opposite, its antiparticle. These are called virtual particles. They are ghostly twins born from the energy of the void, destined to find each other almost instantly and annihilate, repaying the energy loan and vanishing back into the nothingness from which they came. This happens constantly throughout all of space, a silent, flickering storm of creation and destruction that underpins the very fabric of reality. For the most part, this phantom dance goes unnoticed, a balanced cosmic accounting system that always zeroes out. But Hawking asked the crucial question, what happens if this fleeting creation occurs precisely on the razor's edge of an event horizon? Picture the scene: a pair of virtual particles, an electron and its antimatter twin, a positron for example, flicker into existence. In this precarious location, one of the most dramatic possibilities in all of physics unfolds. It is possible for one particle, the positron, to be captured by the black hole's immense gravity falling across the point of no return. Its twin, the electron, however, might be just far enough away to escape, flung out into the wider universe. The pair is now permanently separated. They can never meet again to annihilate. The energy debt can never be repaid in the usual way. To a distant observer, something extraordinary appears to happen. A particle, the electron, has emerged from the vicinity of the black hole. It looks for all the world as if the black hole itself has just emitted something. It is radiating. This escaping particle is no longer virtual. Its lone existence must be paid for by a real source of energy, and the only source available is the black hole itself. To pay for the creation of this newly real particle, the black hole must give up a tiny fraction of its own mass energy, in accordance with Einstein's famous equation E equals mc squared. The escaping particle carries away energy, and in doing so, it steals a minuscule amount of mass from the black hole. This was Hawking's monumental discovery, a revelation that shook the foundations of cosmology. Black holes were not in fact black. They glowed with a faint ethereal light, a thermal radiation born from the strange marriage of gravity and quantum mechanics at their edge. This phenomenon, now known as Hawking radiation, meant that black holes were not eternal prisons after all. They were mortal. Over unimaginable stretches of time, this steady leak of mass would cause the black hole to shrink. Like a cosmic ember left in the freezing void of space, it would slowly, painstakingly radiate its very being away. For a black hole the mass of our Sun, this process would take longer than the current age of the universe by a factor of trillions upon trillions. For smaller primordial black holes, the process could be faster, but the principle was undeniable. Eventually, after an almost infinite cosmic age has passed, the black hole will have radiated away its entire mass, vanishing in a final brilliant flash of gamma rays. It evaporates. It ceases to exist. In this single beautiful piece of mathematics, Hawking had seemingly bridged the gap between the two warring theories. He had applied the quantum to the gravitational and found not a paradox, but a new startling truth. It was one of the greatest intellectual achievements of the 20th century, but in solving one problem, he had unwittingly created a far deeper and more terrifying crisis, a schism in the soul of physics that persists to this day. The implications of his own discovery seemed to lead to a conclusion so profound, so disturbing, that it threatened to bring down the entire edifice of modern science. The problem arises from a simple, devastating question. If the black hole completely evaporates, what happens to all the information it consumed during its long life? Here, we must understand what physicists mean by information. It isn't just the words in a book or the data on a hard drive. In physics, information is the specific, unique quantum state of every particle that makes up an object. It is the complete description of a system, the position, momentum, and spin of every single atom. And according to one of the most sacred, fundamental, and non-negotiable tenets of quantum mechanics, information can never ever be destroyed. This principle, known as unitarity, is the bedrock upon which all of quantum physics is built. It guarantees that if you know the complete state of a system now, you can, in principle, calculate its exact state at any point in the past or future. The universe, at its most fundamental level, remembers everything. Think of it like burning a log in a fireplace. You might think the information that constituted the log, the intricate patterns of its wood grain, its unique cellular structure, is destroyed, but it isn't. It has simply been transformed and scrambled. The information is now encoded in the chemical composition of the ash, in the pattern of the smoke, in the thermal radiation of the heat, in the light of the flames. A sufficiently powerful supercomputer could, in theory, track every single particle and reverse the process, reconstructing the log perfectly. The information isn't gone, it's just incredibly difficult to read. The cosmic book has been rearranged, but no pages have been torn out. Hawking radiation, however, seemed to suggest that black holes are the universe's ultimate paper shredders, capable of tearing out the pages and burning them to absolute nothingness. According to Hawking's initial calculations, the radiation that escapes is purely thermal. It's random. It contains no trace, no echo of the objects that fell into the black hole. A black hole that swallowed a star would evaporate and produce the exact same kind of featureless radiation as a black hole that swallowed an equal mass of encyclopedias or spaceships or dust. The unique quantum information that defined those objects would fall into the singularity, and then as the black hole evaporated, it would simply vanish forever, wiped from the universe with no trace of its existence left behind. This was the crisis. This is the black hole information paradox. It presented physics with an impossible choice between two of its most cherished theories. If Stephen Hawking was correct, then one of two things had to be true. Either general relativity was wrong in its description of black holes, or the fundamental principle of information conservation in quantum mechanics, the very law that ensures cause and effect, that preserves the link between past and future, was wrong. If information can be truly and utterly destroyed, then the universe is not predictable. The past is not recoverable. It would mean that at the heart of these gravitational monsters, a process exists that fundamentally undermines the logical, deterministic nature of the cosmos. It would be like discovering that reality has a delete key, and we have no idea why or when it gets pressed. Hawking himself, a man who had built his career on the elegant certainty of physical law, was forced into the uncomfortable position of a revolutionary. For decades, he stood firm in his belief when a black hole dies, the information within it dies too. He had built a bridge between the two great theories of physics, only to watch that bridge lead over a cliff. He had discovered the process by which black holes fade away, but in doing so, he had seemingly proven that they are cosmic crime scenes where the most fundamental law of the quantum world is violated with impunity. The battle lines were drawn. Physicists were divided into two camps. On one side were the relativists, including Hawking, who trusted the elegant geometry of space-time and were willing to sacrifice a piece of quantum mechanics. On the other were the quantum theorists who refused to abandon the conservation of information, believing it to be more fundamental than gravity itself. They argued that there must be something wrong with Hawking's calculation, some subtle effect he had missed, some way for the information to escape the black hole's grasp before it vanished. For them, the universe simply could not be a place that forgets. The paradox became a crucible, forcing scientists to question their most basic assumptions about space-time and reality. It exposed a deep and profound ignorance at the heart of our understanding. Was Hawking right? Had he uncovered the universe's fatal flaw, a crack in its logical foundation? Or was there a deeper principle at work? A secret language spoken by space-time itself that could resolve this conflict and lead us to a new, more complete theory of everything. The man who had shown us that black holes could die had also left us with the terrifying possibility that in their death, they take a piece of the universe's soul with them. The search for that missing information would become one of the most profound and desperate quests in the history of science. A hunt for a ghost in the gravitational machine. The paradox was not a gentle riddle whispered in the hallowed halls of academia. It was a wound, a deep septic laceration torn through the very fabric of physics. Hawking's calculation, elegant and undeniable, had placed two of our most fundamental truths on a collision course. and the universe itself did not seem large enough for the both of them to survive the impact. On one side stood quantum mechanics, the strange and luminous rulebook of the very small, with its most sacred commandment: information can never ever be destroyed. It can be shuffled, scrambled, encrypted, or hidden, but the universe at its core must keep a perfect record. Every particle, every interaction, every fleeting thought that crosses your mind is a thread in a cosmic tapestry that cannot be cut. This principle, known as unitarity, is the bedrock of causality, the guarantee that the past logically flows into the present, which in turn determines the future. To abandon it would be to accept a universe where events could happen without reason, where the cosmos itself could suffer from a kind of amnesia, forgetting the state it was in just a moment before. On the other side stood Albert Einstein's greatest triumph, general relativity. It painted a picture of space-time as a smooth, dynamic, and continuous stage upon which the drama of the cosmos unfolds, governed by the elegant curvature of gravity. And central to this vision was the equivalence principle, the simple yet profound idea that the laws of physics are the same everywhere. For our purposes, it meant that falling through an event horizon should be utterly unremarkable. There is no signpost, no cosmic gate, no dramatic change to signal your passage into oblivion. From your perspective, freely falling across that boundary would feel like nothing at all, a moment of serene passage into the unknown. This was the no-drama promise of Einstein's universe. Hawking's radiation forced a choice between these two pillars of understanding. If the radiation was truly thermal and random as his math suggested, then the information of the star that collapsed, of anything that ever fell in, was being systematically erased from existence. Unitarity, the soul of quantum theory, was violated. But if the information somehow escaped encoded within that faint quantum whisper, then something violent and extraordinary had to be happening at the event horizon, a place Einstein swore was utterly ordinary. The equivalence principle would be shattered. Physicists found themselves staring into an intellectual abyss, forced to decide which of their children to sacrifice. It was an impossible, agonizing choice, and for decades the community felt paralyzed, caught in a state of suspended disbelief. They probed the edges of the paradox, hoping for a loophole, a subtle miscalculation in Hawking's original work. There was none. The logic was a flawless, ironclad trap. The crisis ignited a desperate search, a period of brilliant and sometimes reckless creativity, as the world's greatest minds threw everything they had at the problem. They were no longer just describing the universe. They were trying to save it from its own logical contradictions. The first wave of proposed solutions were acts of subtle rebellion, attempts to patch the wound without performing radical surgery on the patient. One of the most prominent and for a time most promising of these ideas was the concept of black hole remnants. The idea was beguiling in its simplicity. Perhaps the theory went a black hole doesn't evaporate completely into nothingness. Perhaps after eons of slowly leaking Hawking radiation, after shrinking from the mass of a star to the mass of a mountain, then a car, then a grain of sand, it doesn't just vanish in a final puff of gamma rays. Instead, what if it leaves something behind, a tiny, indestructible nugget no larger than a Planck length, the fundamental quantum pixel of space itself? This would be the remnant, a cosmic ghost containing a secret. Proponents imagined these remnants as the universe's most secure hard drives, hyper-compressed caskets of information. Within this single infinitesimal point, every detail of the original collapsed star, every astronaut who fell across the horizon, every particle's spin, charge, and momentum would be perfectly preserved. The information wouldn't be lost. It would just be locked away in the universe's most extreme form of solitary confinement. On the surface, it seemed to solve everything. The black hole could radiate away its mass as purely thermal random energy, just as Hawking predicted, preserving Einstein's smooth, drama-free event horizon. And at the very end of time, the leftover remnant would stand as a quiet testament that the quantum ledger was still perfectly balanced. Information was safe. Unitarity was upheld, but as physicists dug deeper into the mathematics, this elegant solution began to reveal a monstrously ugly underside. The problems were subtle at first, then overwhelming. Consider the sheer amount of information a black hole can swallow over its lifetime. A single supermassive black hole can consume billions of stars. To store the unique configuration of every single one of those stars, the remnant couldn't just be a generic particle. It would need to be a unique object for every possible black hole history. The remnant of a black hole that only consumed hydrogen would have to be different from one that consumed a neutron star. One that swallowed a library would need to be different from one that swallowed a spaceship. You would need a near infinite number of different times of stable Planck-sized particles. Our current understanding of physics, the Standard Model, has a small, tidy number of fundamental particles. The remnant hypothesis demanded that we accept the existence of an endless, arbitrary zoo of them, one for every conceivable thing that could ever fall into a black hole. Physics abhors such boundless complexity. It felt less like a discovery and more like sweeping an infinite amount of dirt under an infinitesimally small rug. Worse still, how would this information ever be retrieved? If the remnant is stable, the information is locked away forever, which for all practical purposes is no different from it being destroyed. If it could decay, releasing its stored data, the process would be so mind-bogglingly slow and energetic that it would violate other established physical laws. It was an ad hoc fix, a patch that created more problems than it solved. The idea of remnants, once a beacon of hope, slowly faded, leaving the community back where they started, staring into the same terrifying abyss. The wound remained open, festering. The stalemate persisted for years, a cold war between quantum mechanics and general relativity, fought in the silent abstract language of equations. Then, in 2012, 4 physicists dropped a bomb. Their names were Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS. They didn't propose a comforting solution or a clever patch. Instead, they took the existing principles of both theories, the very ones everyone was trying to reconcile, and pushed them to their absolute logical and horrifying breaking point. They published a paper not with a title that suggested a gentle resolution, but one that sounded like a declaration of war, black holes, complementarity, or firewalls. Their work was a thought experiment, but one with the force of a physical proof. It was a trap from which there appeared to be no escape. They began by assuming that the old guard was right, that information did in fact escape a black hole perfectly preserved in the Hawking radiation. They accepted the principle of unitarity without question. This meant the radiation couldn't be random. The photons and particles trickling away from the black hole over billions of years had to be intricately correlated with one another, weaving a complex, scrambled message that contained the full story of everything that had ever fallen in. Let's trace the logic, for it is here that the fuse is lit. Imagine a black hole that is more than halfway through its evaporation. Let's call an early emitted particle of Hawking radiation now far away from the black hole particle A. For the information to be preserved, a newly created particle of radiation, particle B, just about to escape the event horizon, must be quantum mechanically entangled with particle A and all the other radiation that has already left. This entanglement is the very mechanism that carries the information out. Particle B is the missing piece of the puzzle that allows us to reconstruct the book that fell in long ago. So far, so good. But now AMPS asked us to look at particle B from another perspective. According to our understanding of quantum field theory, particle B did not just appear out of nowhere. It was created as one half of a particle-antiparticle pair right at the edge of the event horizon. Its twin particle C fell into the black hole while particle B escaped. This process of pair production demands that particle B and its interior twin particle C must also be inextricably entangled. Their fates are linked, their properties are perfectly correlated. This is the very source of Hawking radiation itself. And here, in this simple picture, is the catastrophe. AMPS pointed out that the escaping particle, our particle B, was now required to be fully entangled with 2 separate independent systems at the same time. It had to be entangled with the early radiation particle A to carry the information out and satisfy unitarity. And it simultaneously had to be entangled with its interior twin particle C to have been created in the first place and satisfy our understanding of space-time. This is a profound violation of a fundamental law of quantum mechanics. It is called the monogamy of entanglement. A quantum system can be fully entangled with one partner and one partner only. It cannot serve 2 masters. It's like saying a coin can simultaneously land on heads to satisfy one observer and tails to satisfy another. It is a stark, unambiguous mathematical impossibility. You have three assumptions on the table. 1. Information escapes, so B is entangled with A. 2. The event horizon is an ordinary place, so B is entangled with C. 3. Entanglement is monogamous. The brutal conclusion of the AMP's paper was that you could have any two of these statements, but you could not, under any circumstances, have all three. They were mutually exclusive. The physics of our universe was fundamentally inconsistent. One of these pillars had to fall. But AMPs didn't stop there. They proposed a solution. A terrifying, violent, heretical solution. What if they asked the monogamy of entanglement is the law that holds supreme? What if nature, when forced into this impossible quantum love triangle, makes a brutal choice? Their proposal was that the moment a particle pair is created at the horizon, the universe instantly and violently severs the entanglement between the infalling and outgoing particles. The bond between particle B and particle C is annihilated to preserve the older, more important entanglement between particle B and the radiation that has already escaped. But breaking a quantum entanglement bond is not a gentle act. It requires an enormous amount of energy. The result of severing this connection over and over again for every particle pair would be to create a shell of catastrophically high-energy quanta, a seething incandescent membrane of pure energy plastered directly onto the event horizon. This was their proposal, a firewall, a wall of literal fire at the gates of oblivion. If you were the astronaut falling towards the black hole, this would change everything. Einstein's promise of a gentle, unremarkable passage would be a lie. The no-drama horizon would become the most dramatic place in the entire universe. The instant you touched the event horizon, you wouldn't slip quietly through. You would slam headfirst into a celestial blowtorch burning at an almost infinite temperature. You would be incinerated in a fraction of a yoctosecond, your constituent atoms torn apart and plastered as a scorched film across the surface of the black hole. There would be no journey to the singularity, no stretching and spaghettification. There would only be annihilation at the border. This was not just a new theory, it was an act of intellectual demolition. It preserved quantum mechanics, but it did so by taking a sledgehammer to the foundations of general relativity. The firewall hypothesis ignited a schism in the physics community unlike anything seen in generations. It was a civil war. Lines were drawn in the cosmic sand. Conferences became battlegrounds, with theoretical physicists, normally colleagues, engaging in fierce, passionate debates that echoed through lecture halls. The community fractured into camps, each defending a different pillar of reality. On one side were the guardians of Einstein's legacy. They found the firewall abhorrent, a monstrously ugly concept that violated the pristine geometric beauty of relativity. For them, the smoothness of space-time was non-negotiable. To place a wall of fire at the horizon was to suggest that the laws of physics themselves were not universal, that they could break down arbitrarily at a specific location in empty space. They argued that something else had to give, perhaps some subtle unknown feature of quantum gravity that we had not yet discovered. They were willing to question the very nature of quantum mechanics itself before they would sacrifice the geometric soul of relativity. On the other side were the quantum purists. They argued that the AMPS logic was simply too powerful, too direct to be wrong. The monogamy of entanglement was not some esoteric suggestion. It was a cornerstone of the quantum world proven again and again in laboratories on Earth. To them, clinging to the no-drama principle in the face of such a stark contradiction was an act of faith, not science. They saw the firewall not as an ugly scar, but as a stunning and necessary consequence of putting our most successful theories together. It was a clue, a harsh and brilliant signpost pointing the way towards a deeper reality. The debate raged with no resolution in sight. The firewall was a paradox in its own right, an idea that seemed both logically necessary and physically absurd. It was the ultimate diagnostic tool, forcing every physicist to confront the cracks in our understanding of the universe and decide which part of reality they were willing to abandon. The problem of information loss had led us to an impossible crossroads. One path led to a universe that forgets its own past. The other led to a universe with a wall of fire at the edge of space-time. Neither destination was a place we thought we were going. The search for a third path, a way to navigate between these two apocalypses, became the single most urgent quest in fundamental physics, a desperate hunt for a new idea, powerful enough to heal the schism and stitch the fabric of reality back together. And so the paradox was complete, a perfect and terrible circle. A law of nature as fundamental as gravity itself had been pitted against Hawking's own brilliant calculations. Information, the universe's most basic currency, the very essence of everything that has ever been, was being systematically, utterly annihilated. Physics had led us to a cliff edge, an intellectual abyss from which there appeared to be no return. If a star, a planet, or even your own memories were to fall into a black hole, they would not just be crushed, they would be erased from the cosmic ledger forever, as the black hole slowly, inexorably evaporated into nothing. This was not a minor disagreement among theorists. It was a declaration of war on the logical foundation of reality, and for 2 decades the silence from the abyss was deafening. Science seemed to be telling us that our universe at its core made no sense. But from the fringes of theoretical physics, a rescue mission was being mounted, led by 2 physicists who refused to let the universe succumb to such a deep and pervasive amnesia. Gerard Hooft in the Netherlands and Leonard Susskind in America, working independently, began to formulate a defense of cosmic memory, an idea so profoundly strange, so contrary to our every intuition about space and dimension, that it felt more like a mystical revelation than a scientific theory. The solution they converged upon would not just solve the paradox, it would force us to question the very fabric of the world you see around you, the solidity of the ground beneath your feet, and the 3-dimensional space you inhabit. They proposed that the universe had a secret, a hidden layer of reality that we had overlooked entirely. They called it the holographic principle. To understand this audacious idea, you don't need to look to the farthest reaches of the cosmos. You only need to look inside your wallet, take out a credit card or any modern identification and tilt it in the light. You will see a small shimmering square, a hologram. It appears to be a flat 2-dimensional sticker, a simple metallic film. Yet, as you move it, a 3-dimensional image emerges, a bird taking flight, a globe spinning a face turning to meet your gaze. The illusion of depth, of volume of a solid object existing in space is a complete fabrication. All the information required to construct that 3-dimensional world is entirely encoded on that impossibly thin 2-dimensional surface. Scratch the surface and you damage the image. Destroy the surface and the 3-dimensional ghost vanishes with it. The 3D world in this case is just a projection, a phantom generated by a flat plane of information. Now take that simple, familiar concept and apply it to the most extreme, most alien object in the entire universe, a black hole. The information paradox was born from the belief that when you throw something into a black hole, say an encyclopedia, it passes through the event horizon and plunges towards the singularity, taking its volumes of information with it into a region of infinite density. The holographic principle makes a staggering counterproposal. It suggests that the encyclopedia and the information it contains never truly crosses the event horizon at all. Instead, as the object approaches that point of no return, its fundamental information content gets stuck. It becomes imprinted or smeared across the 2-dimensional surface of the event horizon itself, like a bug hitting a cosmic window pane. The 3-dimensional object is gone, seemingly fallen into the abyss, but its ghost, a perfect, complete informational record of its existence, is now encoded on the boundary of the black hole. Every atom, every quantum spin, every letter on every page of that encyclopedia is translated into a complex 2-dimensional mosaic spread across the entire surface of the horizon. Think of the event horizon not as a gateway, but as a screen, a cosmic storage device of unimaginable density. The 3D world that falls in is like the object being recorded. The 2D event horizon is the recording medium itself. The information isn't lost. It was never inside the black hole to begin with. It's on the times outside, times clinging to the edge, a shimmering holographic record of everything the black hole ever swallowed. This single radical shift in perspective vaporizes the paradox. If the information never enters the region that evaporates, it can't be destroyed when that region disappears. It remains held in trust on the boundary of space-time. This wasn't just a wild guess or a philosophical flight of fancy. It was rooted in a profound clue that had been hiding in plain sight for years in the work of Israeli physicist Jacob Bekenstein. Long before this debate raged, Bekenstein had been pondering the entropy of a black hole, a measure of its disorder, which in physics is directly equivalent to its information storage capacity. Intuitively, we expect the information capacity of any object to scale with its volume. A bigger warehouse can hold more boxes. A bigger hard drive can hold more data. A bigger black hole, one would assume, could hold more information. But Bekenstein's calculations revealed something deeply bizarre. A black hole's entropy, its total information content, was not proportional to its three-dimensional volume. It was proportional to the two-dimensional times area times of its event horizon. This was the smoking gun. It was as if you discovered that the capacity of a library was determined not by the number of shelves inside it, but by the surface area of its exterior walls. It made no logical sense in a three-dimensional world. Why would the universe's ultimate storage device file everything on its surface rather than filling up its interior? Bekenstein's discovery was the first mathematical tremor that suggested reality was not what it seemed. It whispered that for a black hole, the inside story was a distraction. The real story, the complete story, was written on the cover. The holographic principle took this strange mathematical quirk and elevated it to a law of nature. It declared that there is a fundamental limit to the amount of information that can be packed into any region of space, and that limit is always defined by the surface area that encloses it, not the volume it contains. The universe, it seems, has a maximum resolution, a fundamental pixel size for reality known as the Planck area. You can't cram more than one bit of information into a tiny square on a surface measuring 1 Planck length on each side, and a black hole's event horizon is a surface that is perfectly maximally saturated with these bits. It is the most efficient information storage surface allowed by the laws of physics. So the information is safe, tattooed onto the skin of the black hole. But this only solves half the problem. If the black hole evaporates via Hawking radiation, how does that information get times out times? How does the story written on the event horizon get re-released back into the universe for the cosmic archives? This is where the hologram truly comes to life. Hawking's original calculation assumed the radiation was purely thermal, a featureless random hiss of particles with no message to convey. It was like the meaningless static from an untuned radio. But the holographic principle insists that this static is anything but random. It is in fact an incredibly subtle, intricately encoded signal. The escaping Hawking particles are not generated in a vacuum of nothingness. They are born right at the edge of the event horizon, the very surface where all that information is stored. As a particle-antiparticle pair is torn apart at the boundary, the escaping particle is not truly independent. It is subtly quantum mechanically entangled with the holographic data imprinted on the horizon. Imagine the event horizon is a vast burning library, and the books are the information of everything that fell inside. Hawking radiation is the smoke pouring from this library. At first glance, the smoke appears to be a chaotic, meaningless byproduct of the fire. But if you could analyze every single particle of soot, every molecule of carbon, every photon of heat with impossible precision, you could, in principle, reconstruct the books that were burned. You could figure out the chemical composition of the ink, the fibrous structure of the paper, the very words on the page. The information is not lost. It is just scrambled, translated into a different, much more chaotic form. The Hawking radiation, according to this new understanding, is the cosmic smoke. As the black hole slowly shrinks, its surface area decreases. The holographic plate itself is getting smaller. To do so, it must shed the information it holds. Each particle of Hawking radiation that escapes carries away one tiny, infinitesimally small piece of the original hologram. A single photon might carry the information about the spin of one electron from a single atom in a single star that fell in 1 billion years ago. The process is excruciatingly slow, agonizingly complex. The information comes out, but it is shredded, encrypted, and broadcast across trillions of particles over eons of time. By the time the black hole has completely evaporated, leaving behind nothing but a final puff of radiation, the entirety of the holographic plate has been broadcast back into the cosmos. Every bit of information that ever fell in is now encoded in the subtle correlations between those outgoing particles. Nothing was destroyed. The universe remembers everything. The law is upheld. The battle was won. Hawking, confronted with the elegant mathematics of und Hooft Susskind, and others famously conceded his decades-old bet. The information paradox, it seemed, was resolved, but in science every answer is merely the key to a more bewildering door. And the door this solution unlocked leads to the most vertigo-inducing concept in the history of human thought. Physicists began to ask a deeply unsettling question. If a black hole, the most compact three-dimensional object imaginable, can be fully described by a two-dimensional surface, then what does that imply about the rest of the universe? What does that imply about us? If the ultimate expression of gravity and space-time can be a hologram, perhaps times everything times is, the logic is terrifyingly simple. What if our vast three-dimensional cosmos with its 100 billion galaxies stretching across billions of light-years is itself just a projection? A magnificent complex illusion generated by information stored on a distant, two-dimensional boundary at the edge of our reality. This is the grandest implication of the holographic principle. Not just that black holes have holographic surfaces, but that our entire universe might be a cosmic hologram. You, the room you are in, the planet you stand on, the stars you see in the sky, all of it could be the 3D manifestation of information written on some colossal, unknowable cosmic horizon. This is not mere philosophical speculation. It is a serious theoretical framework born from the unforgiving mathematics of string theory and quantum gravity. It suggests that the true reality, the fundamental reality, is a flat, lower dimensional plane, and our perceived universe is its ghostly projected image. Scientists are even searching for evidence. They reason that if our 3D world is a projection from a pixelated 2D surface, then space-time itself should not be perfectly smooth. At the smallest possible scales, we should find a fundamental fuzziness, a graininess, a limit to the resolution of reality, just as a projected image breaks down into pixels if you look too closely. Experiments at facilities like Fermilab have been hunting for this holographic noise, a slight jitter in space-time itself, the signature of our universe's cosmic projection screen. So far the search has come up empty, but the quest continues, driven by the sheer mind-altering possibility that we are living inside an illusion so perfect, so seamless, that we have only just begun to suspect its existence. We had stared into the abyss of the information paradox, a place where the laws of physics broke down and declared the universe nonsensical. And we were rescued by an idea that suggests the universe as we know it isn't even real in the way we think it is. To save the integrity of information, we had to sacrifice the solidity of the world itself. The information isn't destroyed, it's preserved on a holographic plate. It escapes painstakingly encoded in the dying whispers of Hawking radiation. The encyclopedia is not gone forever. Its story is now written in the language of light and energy scattered across the cosmos. But even this fantastically strange and beautiful solution contains its own dark secrets, its own hidden paradoxes. For if you could collect every single particle of that Hawking radiation over trillions of years and piece the story back together, what would that recovered information tell you? Would it be a perfect copy of the original? And what would happen if you yourself tried to cross the event horizon to witness this holographic imprinting firsthand? Physicists who tried to answer that question stumbled upon a new nightmare. A wall of fire, a quantum inferno at the edge of the black hole that would incinerate anything on contact. The theory that saved information has given birth to a monster, and in doing so has revealed that our understanding of these cosmic titans and the very nature of space-time is still terrifyingly incomplete. The abyss, it seems, has more than one edge, and so the paradox that began in the crushing dark of a black hole's heart refuses to stay contained. It spills out, leaking from the event horizon not as radiation but as a question that infects everything. If the soul of a three-dimensional star, all its history and complexity can be perfectly encoded on a two-dimensional surface, then we've stumbled upon a law of physics far more profound and terrifying than we ever imagined. We thought we were studying an anomaly, a bizarre exception to the rules of the cosmos, found only in its most violent corners. But the chilling question that kept physicists awake at night was this: what if the black hole isn't the exception? What if it's the blueprint? What if this holographic principle, this bizarre marriage of information and geometry, applies not just to fallen stars, but to the entire universe itself? To even begin to entertain this notion is to feel the solid ground of reality turn to mist beneath your feet. Because for you, for all of us, the universe has a reassuring solidity. It has depth. You can reach out your hand and feel the space between you and the world, forward and backward, left and right, up and down. These three dimensions are not an opinion. They are the axiomatic foundation of our existence, the very stage upon which the drama of life of stars of the comet 3I, Atlas hurtling towards our future, plays out. Yet the mathematics that saved reality from the black hole information paradox now returns with an audacious, almost blasphemous proposition. It suggests that one of our dimensions, the very depth we perceive as real, might be a phantom, a clever, persistent, and utterly convincing illusion. Think of the edge of our own cosmos. Not a wall, not a barrier, but a boundary of light and time known as the cosmological horizon. It is the farthest we can possibly see, the point beyond which the light from ancient galaxies has not had enough time in the 13.8 billion years of cosmic history to reach us. To us, it is the ultimate boundary. We treat it as the edge of our observable bubble, but the holographic principle forces us to see it in a new, horrifying light. What if that distant, shimmering sphere isn't just a limit to our vision? What if it is the universe's own event horizon? A surface that contains within its two-dimensional fabric every single bit of information required to project the grand three-dimensional spectacle we call home. What if we are living inside the hologram, while the real machinery, the cosmic film, is playing out on a screen billions of light years away? This isn't poetry or philosophy. It is a conclusion born from a desperate calculation. When physicists Gerard Hooft and Leonard Susskind extended the logic of black holes to the universe, they tried to tally up the total amount of information, the entropy that our cosmos could possibly hold. It's a measure of everything. Every particle, every star, every thought, every possible state of every single thing within our cosmic horizon. Their first attempt, the intuitive one, was to calculate this information based on the volume of the universe. They treated space as a vast container, a three-dimensional box, and tried to figure out how many fundamental bits of data could be crammed inside. The number they got was catastrophic. It was an absurdity, a mathematical scream. It was so titanically impossibly large that it predicted the universe should have collapsed under the gravitational weight of its own energy and information, forming a black hole of unimaginable scale the instant it was born. Our very existence proved their calculation was wrong. The universe is not a black hole. It is stable. It is expanding. It is here. So the information couldn't be stored in the volume in the 3D space we so intimately know. Something was fundamentally broken in our understanding of space itself. Then they tried another way. Guided by the eerie precedent of the black hole, they performed the calculation again, but this time they ignored the volume entirely. They threw out the illusion of depth and treated the universe as a flat, two-dimensional surface. They calculated the maximum information that could be tiled bit by bit across the vast surface area of our cosmological horizon, that distant boundary marking the edge of what we can know. They were calculating the data capacity of the universal screen, and the answer they found sent a shockwave through the world of physics. It was a perfect match. The number was finite. It was enormous, yes, but it was sensible. It precisely matched the amount of entropy our universe appears to have. The math worked, but only if you made a terrifying assumption that everything happening times in here, times in the grand 3D theatre of the cosmos, is nothing more than a projection of information written times out there times on the 2D boundary. Let that sink in. The equations that govern the universe demand that the third dimension is in some fundamental informational sense redundant. All the data needed to construct you, the chair you're sitting in, the planet beneath you, the Milky Way galaxy, and the path of the incoming comet 3I, Atlas, all of it can be fully described by a code written on a distant two-dimensional surface. We are the three-dimensional ghosts, projected from a two-dimensional machine. The feeling of depth, the space between your eyes and the screen, the very notion of place it, is all an emergent property, a clever trick of the cosmos. Like the image of a princess beamed from a droid in a science fiction film, we are a tangible apparition whose source code exists elsewhere. This reshapes everything we thought we knew about the fabric of reality. For centuries, we have imagined the universe as a great clockwork mechanism, a stage on which physical objects governed by immutable laws interact. An atom in your body and an atom in a distant star are separated by a vast, real gulf of space. But in a holographic universe, this concept of separation of locality becomes fragile. If you and that distant star are merely projections from a shared 2D source, you are connected in a way classical physics can barely comprehend. You are, in a very real sense, adjacent to each other on the underlying cosmic hard drive. The information that defines you and the information that defines it might be neighboring bits of data on that ultimate boundary. This isn't just a bizarre theory, it's a potential explanation for some of the deepest weirdness in quantum mechanics, like entanglement, where two particles can be instantaneously linked across any distance, defying the cosmic speed limit. In a hologram, they are never truly far apart. Their source code is right next to each other. What would such a reality look like if our universe is a projection it cannot have infinite resolution? Any projected image is made of fundamental building blocks, like the pixels on a screen, or the grains of silver halide on a photographic film. Up close, the smooth illusion breaks down, revealing the discrete, granular nature of its construction. The holographic principle predicts that our space-time should be the same. It suggests that if you could zoom in to the smallest possible scale, a scale so minuscule it makes an atom look like a galaxy, you would find the pixel of reality. This is the Planck length, about 100 million trillion times smaller than a proton. At this unfathomable resolution, the smooth, continuous fabric of space and time would dissolve into a shimmering grid of discrete bits, a quantum foam where the concepts of here and there, now and then, cease to have any meaning. This is the ultimate scaffolding of existence, the Planck scale pixel, from which the entire illusion of our three-dimensional world is rendered. Every motion you make, every thought that flickers through your mind would correspond to a shifting pattern of these fundamental bits on the cosmic horizon. The inexorable flow of time itself might be nothing more than the universe processing this cosmic code, calculating the next frame of the hologram, one Planck time at a time. Our past, present, and future might already be written, encoded on that universal boundary, with our consciousness merely experiencing the playback. This transformation of reality from a physical stage to an informational process is the most profound paradigm shift in the history of science. It reframes the universe not as a collection of matter and energy, but as a vast quantum computer. And the output of its computation, everything we have ever known, the implications reverberate far beyond the sterile halls of physics, touching the very core of our identity. What are you in such a world? Are you a physical being? A collection of atoms moving through real, tangible space? Or are you a complex data stream, a symphony of information so intricate that it generates the illusion of consciousness, of free will, of love, and of fear? When you look up at the night sky, are you seeing a universe of profound physical depth, or are you looking at the impossibly high-resolution output of a cosmic projector? With the light from the stars being part of the beam that helps form you, it's a dizzying, disorienting thought. It suggests that the solid world is a collaborative hallucination baked into the source code of the cosmos. And in this strange new light, even the impending threat of 3I, Atlas, takes on a different character. We see it as a physical object, a mountain of ice and rock on a collision course with our world governed by the brute force of gravity. In a holographic reality, it is that, but it is also something more. It is a cascading sequence of bits, a flaw in the code, a destructive subroutine running on the universal computer whose projected manifestation is an agent of annihilation. Does that make the threat any less real? No. The pain of its impact, the end of our civilization, would be just as total. The suffering would be written into the information just as surely as the joy. The hologram is for all intents and purposes our reality. Its rules are our rules, its fate is our fate. But knowing the potential architecture of this reality grants us a new, albeit terrifying perspective. It tells us that the universe is stranger, more interconnected, and more mysterious than we ever dared to believe. It whispers that the fundamental substance of the cosmos might not be matter or energy, but information, the it from the bit. This is a concept so powerful it threatens to unify the physical world of general relativity with the strange informational world of quantum mechanics. It offers a potential path to a theory of everything, a single framework to describe all of creation, from the Big Bang to the flickering of a single neuron. The price for this ultimate knowledge, however, is the sacrifice of our most cherished belief that the world we see is the world as it truly is. We are forced to confront the possibility that we are living in a grand cosmic simulation, not one run by a hidden intelligence, but one generated by the fundamental laws of physics themselves at the edge of space and time. This isn't just an intellectual exercise, it's a testable idea. If our world is a grainy, pixelated projection, then that granularity, that fundamental jitteriness of space-time might be detectable. It would manifest as a constant faint noise in the fabric of reality, a fundamental uncertainty in the position of all things, as the universe struggles to render a smooth 3D image from a finite 2D code. This is not the quantum uncertainty we already know. This would be a new intrinsic holographic noise, the hum of the cosmic projector. And for years, deep within the Earth, scientists have been building instruments of almost unimaginable sensitivity devices, designed not to look out at the stars, but to listen for the subtle crackle of space-time itself, straining to hear the faint, insistent whisper that would finally confirm our deepest fear and our most incredible truth that our solid three-dimensional universe is not the territory but merely the map. And so the cosmic hologram comes into focus. What we are left with is not an answer but a profound transformation of the question itself, a reimagining of reality so complete, so utterly radical, that it forces us to reevaluate everything we thought was solid, everything we've believed was fundamental. It has been a journey of staggering intellectual distances, a voyage that began with the simple, visceral image of a celestial body, the comet 3I, Atlas hurtling through the dark. We watched it, a fragile ball of ice, and rock a transient visitor from the cold outer darkness of our solar system as it approached its own ultimate boundary, a Roche Limit, a point of no return, an invisible line in space where the universe's most fundamental force, gravity, would turn from a gentle shepherd into a merciless executioner, tearing it apart with tidal shears. That single dramatic event, a cosmic spectacle of destruction, became our gateway. It was the perfect earthly metaphor for a far deeper, far more consequential limit we were destined to explore together. The Roche limit of a comet foreshadowed the event horizon of a black hole. The tidal forces that would shred a wandering piece of ice were but a whisper of the gravitational power that bends light, stops time and tears at the very fabric of space-time itself. We used this cosmic object lesson to catapult ourselves from the familiar neighborhood of our sun to the most extreme environments the universe has to offer, to the very edge of physical law. And there, at that ultimate precipice, we found not an end but a beginning. We found a paradox. Our entire investigation, this odyssey into the heart of reality, has revolved around these gravitational behemoths. We came to understand black holes not as mere cosmic vacuum cleaners, but as the universe's ultimate laboratories. They are the crucibles where our two great pillars of 20th century physics, Einstein's general relativity and the quantum mechanics of the very small, are forced into a violent, unavoidable confrontation. Everywhere else in the cosmos, they coexist peacefully in their own domains. Relativity choreographs the grand ballet of galaxies and planets, a smooth, continuous waltz of warped space-time. Quantum mechanics governs the frenetic, uncertain dance of particles, a world of probabilities, discrete packets of energy, and ghostly superpositions. But inside a black hole at its singularity, these two irreconcilable descriptions of reality must somehow apply to the same patch of existence. The infinitely dense must be described by the physics of the infinitesimally small. The smooth fabric of space-time must contend with the chaotic fizz of quantum foam. It is a place where our physics breaks, a place where the universe demanded we do better. And from that demand, born from the silence and darkness of an event horizon, the information paradox emerged. It was more than just a scientific puzzle. It was a philosophical crisis that struck at the heart of causality, at the very notion that the past uniquely determines the future. The dilemma, as we've seen, was terrifying in its simplicity. Quantum mechanics, the most successful theory in the history of science, is built on an unbreakable foundation. Information can never ever be truly destroyed. It can be scrambled, hidden, or rearranged into a form so complex we can never hope to decode it, but its fundamental essence must persist. Yet Stephen Hawking's monumental discovery revealed that black holes are not eternal. They evaporate, bleeding their energy back into the cosmos as a faint thermal hiss of random particles, a form of radiation utterly devoid of the rich, intricate details of all the matter that fell inside. A star with 1 billion years of history, a library containing all the knowledge of a civilization, your own cherished memories. If they were to fall into a black hole, they would, according to Hawking's initial calculations, be reduced to the same featureless thermal static. The information would be gone, utterly and completely annihilated. This was the great conflict, the intellectual war that defined a generation of physics. It was a contradiction so profound it couldn't be ignored or swept under the rug. It was a flaw, a crack in the edifice of our understanding so deep that it threatened to bring the whole structure crashing down, and like all great scientific crises, it became a catalyst of unparalleled power. It was the irritant in the oyster, the cosmic grit that forced the greatest minds on the planet to secrete new layers of thought, new principles, new ways of seeing the universe, until a pearl of profound beauty and strangeness began to form. This paradox was not a sign of failure. It was an invitation. It was the universe pointing a finger at a specific place and saying, "Look closer. Your cherished beliefs are wrong. Dig here." And so they dug. For decades, physicists on all sides of the debate battled with ferocious intensity. They filled blackboards with equations so complex they seemed to have a life of their own. They conducted thought experiments that pushed logic and imagination to their breaking points, envisioning quantum computers falling into singularities and observers being stretched across event horizons. They argued, they collaborated, they challenged one another's most fundamental assumptions. It was a struggle not just for the soul of physics, but for the nature of reality itself. And out of this intellectual fire, the radical new vision was forged. The solution, when it began to emerge, was more shocking than the problem. The warring factions of quantum mechanics and general relativity found their peace treaty in the most unexpected of ideas, the holographic principle. This principle, born from the mathematics of black hole entropy, proposes something that still sounds like pure science fiction. It suggests that everything you see, everything you feel, your entire three-dimensional world, might be nothing more than a projection. A complex, shimmering hologram encoded on a distant two-dimensional surface that surrounds us. Like the security chip on your credit card that holds a 3D image on its flat surface, the universe itself may be encoding all the richness and depth of our reality on a distant cosmological horizon. The information that falls into a black hole, according to this revolutionary idea, is not lost. It never truly crosses the event horizon from an outside observer's perspective. Instead, it gets imprinted, smeared, and intricately encoded onto the two-dimensional surface of the horizon itself, like data being written to a cosmic hard drive. The faint Hawking radiation that eventually emanates from the black hole is not random. It is the impossibly scrambled but perfectly preserved information being slowly released to the playback of the data that was stored. Information is saved. Quantum mechanics is preserved. The crisis is averted. But at what cost? The price of this solution is our intuitive sense of reality. Think about what this truly means for you right now. It means that the feeling of depth of distance of moving through a voluminous space is a magnificent illusion. The fundamental reality is not here in this room with you. It is out there written on a boundary surface at the edge of the cosmos. The subatomic particles that make up your body, the neural firings that constitute your thoughts, the very fabric of the space between stars, all of it could be the holographic projection of a simpler, flatter quantum reality. We may be living inside a hologram. Our universe, in its most fundamental description, might not be three-dimensional at all. The third dimension, the one that gives us our sense of place and presence, could be an emergent property, a trick of perspective, generated by quantum information arranging itself on a distant screen. This is the new cosmos that the information paradox has revealed to us. It's a universe that is profoundly interconnected, where a point here is inextricably linked to a point on that distant boundary. It suggests a universe where space itself is not fundamental, but is instead stitched together from the threads of quantum entanglement. The strange, spooky action at a distance that Einstein so famously distrusted, where two entangled particles can influence each other instantaneously across vast distances, might not be so spooky after all. In a holographic universe, those two particles aren't really separated by distance. They are different projections of the same underlying information on the boundary surface. They are, in a fundamental sense, still touching. The paradox has led us to a place where space-time itself is a secondary phenomenon, an echo of a deeper information-based reality. And it is here in this holographic vision that the path toward the holy grail of modern physics finally becomes illuminated. The quest for a unified theory of quantum gravity. For a century, physicists have dreamed of a single, elegant mathematical framework that could unite Einstein's theory of the large with the quantum theory of the small, a theory of everything. The information paradox, by forcing the issue by creating a problem that could only be solved by combining gravity and quantum effects, has acted as our most powerful guide. It has served as a crucible testing the metal of every proposed idea. Any candidate for a theory of quantum gravity, whether it's the vibrating filaments of string theory or the discrete loops of loop quantum gravity, must now pass the black hole test. It must be able to explain from first principles how a black hole's entropy arises. It must show with mathematical certainty how information is preserved. It must be compatible with the holographic principle. The paradox has provided the concrete benchmarks, the non-negotiable requirements that any future theory must meet. It has transformed the search for quantum gravity from a purely abstract philosophical exercise into a concrete problem with tangible constraints. We are no longer just guessing in the dark. The faint glow of Hawking radiation, once thought to be a signal of physics's ultimate failure, has become a beacon lighting the way forward. We are now building a new understanding of the universe from the ground up, an understanding where information is the primary substance. Not matter, not energy, not even space and time themselves, but information. Bits of quantum data entangled and woven together in a vast cosmic network, giving rise to everything we experience as physical reality. We began our story with a simple question: what happens when an object, a comet, gets too close to a source of immense gravity? We saw it disintegrate its structure, overwhelmed, its identity erased. This simple observation launched us on an epic intellectual journey, following that same question down the rabbit hole to its ultimate conclusion. We asked what happens when times anything, times a star, a planet, an idea, gets too close to the ultimate source of gravity, a black hole. And for a time, the answer seemed to be the same: disintegration, erasure, annihilation. But the universe, it turns out, is far more subtle, far more clever, and infinitely more beautiful than that. The information is not lost, it is transformed. It is encoded on a boundary woven into the shimmering fabric of the event horizon and projected back out as the rich, complex, three-dimensional reality we inhabit. The story of a dying star is not erased, it is imprinted onto the very structure of space-time. The legacy of a civilization that falls into a black hole is not forgotten. It is stored in the subtle quantum correlations of the universe itself. Nothing is ever truly lost. This journey has taken us to the absolute limits of human knowledge, to the edge of what we can imagine and what we can calculate. The concepts are dizzying, the implications world-altering, and yet it all began with the most human of instincts: curiosity. It began with looking up at the night sky and wondering, with seeing a point of light moving against the fixed stars and asking, what is that, where is it going, and what laws govern its destiny? That relentless, unyielding spirit of inquiry is our species' greatest gift. It is what drove Hawking, Bekenstein, Susskind, and countless others to challenge the giants who came before them, to question the unquestionable, and to push against the boundaries of the known universe until they cracked. The debate over the information paradox is not over. The fine details of how the hologram works are still the subject of intense research, but the revolution it sparked is irreversible. Physics will never be the same. Our vision of the cosmos and our place within it has been permanently altered. So the next time you stand beneath a clear, dark sky and you look up at the infinite tapestry of stars, remember what you have seen. Remember the journey from a fragile comet to the edge of reality. Remember that the solid ground beneath your feet, the air you breathe, and the very thoughts inside your mind may be the intricate projection of a cosmic code written on the universe's distant edge. You are not just looking out into the cosmos. You may be looking at the very screen from which you are projected. The universe is not a container you live inside. The universe is a story, and you are written into its pages. And the quest to read that story, to understand its language, and to discover its ultimate meaning, that is the grandest adventure of all. It is an adventure that is far from over. In fact, it is just beginning.